let's actually talk about what an antiderivative is. What's the word anti kind of tell you? Not, opposite, okay? An opposite or reverse direction. That's exactly what an antiderivative is. You've got the derivative, and you need to reverse the process and go back and find the function you took the derivative of. Okay? So that's going to be the whole topic. Now, before we actually get started seeing how to do that, I'll give you a reason why you need to know how to do that. Let's get a little bit of light off here. Let's see if we can lighten it up a little bit. Okay, I think that's a little better. So the consumption of energy generated by the wind has really increased since 2001. So over the last 15 or 20 years, it's increased quite a bit because of the increased price of fossil fuels. So in 2001, it was 70 trillion BTUs, and in 2013, it was 1595 big trillion BTUs. So that's quite a bit of increase. And what we want to do with this, using antiderivatives in this chapter, is we're going to estimate wind energy consumption over the period using something called a definite interval. And that's a mathematical concept that measures area under a curve. So that's really what we're using an antiderivative for. Ultimately, is to find the area under a curve or between two curves. The same thing allows us to determine the distance that a car's traveled if we have its speed as a function of time, and how much a bacteria culture will grow, and how much consumers benefit by buying a product at a price determined by supply and demand. That last one is a very important application that we're going to look at. We're going to look at consumer and buyer surplus. So a little bit about what antiderivatives are. Basically, if I just put this in a nutshell, because you've got this part in your notes, an antiderivative says basically if capital F prime of x is equal to some function, then capital F of x is referred to as the antiderivative of the function. We'll see how that works. It's really not a hard process. So for example here, and this actually gets back to one of the test questions that I asked you, where I asked you that I think it was Vanessa was her name, that she thought that because two functions had the same derivative, that meant that the functions were equal to each other. Remember that question? And the correct answer to that question was that she is mistaken, because they can have the same derivative. The only thing the derivative measures is the rate of change of those two functions. So if you're measuring the rate of change of two functions can have the same slope and not be the same function. An easy example, one easier than the one I gave you, that it would have been obvious to Vanessa that they weren't the same, would be if you took the derivative of y equals 6x, and then you took the derivative of y equals 6x plus 7, well, no, those are not the same functions. They're very different functions, but they have the same slope, so they're going to have the same derivative. And that's one of the things that we're going to have to think about in this chapter is, how am I going to distinguish between which one is the right derivative? So if f of x, capital F of x, meaning it's an antiderivative, is 10x, and then f prime of x is 10, what does that mean that capital F of x was? Its parent function, if you want to think of it that way. Well, that means that f of x is something that had a slope of 10. And since the only thing that has a slope of 10 is y equals 10x, then that would be one candidate for the antiderivative. Okay? f of x equals 10x is the antiderivative of f of x equals 10. For f of x equals x squared, its derivative is 2x. So that means x squared is the antiderivative of 2x. This is what you take the derivative of. This is what the derivative turns out to be. So we're going to reverse the process. And actually, we'll eventually stop talking about antiderivatives and call it an integral. So we need to find the antiderivative of 5x raised to the 4th power. So I want, without me showing you how to do it, I want you to think through, how did you come up with that derivative if that had been your derivative? What would we need to do to turn that back into its function? Yeah, because originally we subtracted 1 from the power, right? So we need to add that number back. And then what else did we do with that power? We dropped it down and multiplied by it. So the 5 is in front, which kind of lines up with what we think, because if the actual original exponent had been 5 and we dropped it down in front and subtracted 1 from the 5, we got the 4. So that means then the original function must have been x to the 5th. And you should be able to verify that by taking the derivative of f to the 5th drop the 5 down in front, keep the x, subtract 1 from the power, and we get exactly what we started with, 5x to the 4th. Okay? So if it's a power function, it shouldn't be too hard. It's not too hard to reverse the process. So this is kind of the blueprint for how you do it. Basically, you're remembering that our power rule said that you use n times x to the n minus 1. That means n must have been the 5. And then that means if 5 is n, then n minus 1 is what gave us the 4. So that shows us that x to the 5th is the antiderivative. Now I'm going to jump ahead just a little bit with this and give you an idea. What if the original function had been x to the 5th plus 7? What's the derivative of x to the 5th plus 7? X to the 4th. But is this the same as that? I'm sorry, not that. Is this the same as that function? No. What is it that makes them different? What makes those two functions different? They have the same derivative, but how are the functions themselves different? What's the only difference? The plus 7. What if I change the plus 7 to minus 10? Does that change anything? No. What if I change it to plus 24. Does that change anything? Not on the derivative. It only changes the function. The only thing it changes about the function is it moves the function up and down the y-axis. Makes it have a different y-intercept. That's it. Okay? They're not the same function, but they have the same rate of change. But because this is true, what we're going to see in a few more examples is that when we do an antiderivative, what we do to show that this could be the derivative of several different functions is we're going to add what's called a constant of integration to the derivative, to the antiderivative, which is basically saying the original function had a constant on it, so the antiderivative of this is actually f of x equals x to the fifth plus a constant. So we're going to actually have to add a constant to the antiderivative because this one just happened to be 0. It might be some number, and that's what a constant is. It's just saying you added or subtracted some number, and that number had a derivative of 0. So it didn't change the derivative in it, but it does change the function. So that's just, kind of give you a little heads up. So here's an application problem. Actually, I'm going to try to do this a little differently. Suppose population in millions is growing at a rate given by f of x equals e raised to the x power, where x is the time in years from some initial date. What function would find the population, the value of the population at time x? Because this is, it says it's growing at a rate. That tells you that's a derivative. That tells you f of x is equal to e to the x is the derivative. What is that the derivative of? Get back to your derivative rules. What is e to the x the derivative of? I heard somebody say it. E to the x. So what's the derivative of itself? So since it says find the function giving the population at time x, and the population is measured in million people, then capital F of x, that's how you indicate that it's the function that had its derivative taken. Capital F of x is equal to e to the x million people at x years from the initial date. Notice that there is no million people per year because that's the units that went with its growth rate. Okay? We're finding the original function. Now, the thing is, like I said before, and this is the example that is in the PowerPoint that I use. The derivative of little f of x is capital F of x, which is e to the x. So one possible population function is this one. It all depends on what that initial value was. So in the case that we're looking at, here's what we want to look at about antiderivatives that I mentioned earlier. When we have a function like f of x equals x squared, that's not the only function that has a derivative of 2x. X squared plus 3 has a derivative of 2x. X squared minus 12 million has a derivative of 2x, because that's the rate of change function. So here, all three of these functions, this one is g of x, f of x, and h of x, all three of these functions have that derivative. All three of them do. But they have different y-intercepts, which tells you that they're all basically this function plus or minus a constant. And that constant, since that constant could be positive or negative, we could just say plus the constant. So that's actually how we're going to write our antiderivatives. For any number c, the function capital F of x is equal to x squared plus c is actually the definitive derivative. It's saying, I don't know what c is, but there is potentially a constant that was added to that function. That'll give you the whole family of functions. This is the derivative form. So that's really the only thing that this says, is that if you have two functions that differ by a constant, then their derivatives are going to be the same. That's actually a theorem. So now we'll look at something called a power rule for integrals. If you have the integral, which is the same as the antiderivative, if you have the integral of x raised to any power, and the way that you write an integral or an antiderivative is this is called the integral. It's just a long, skinny kind of an S shape of x raised to some power, and this indicates that whatever this is a derivative. That's all that tells you. You always have to have the dx at the end of it, but this always tells you that whatever that was that came in front of dx, between the integral sign and dx, was a derivative. The way that you do this, and we've already kind of said this, so we're just kind of summarizing it, is that you add 1 back to the power, and then you divide by the power plus 1. Okay? And then you add the constant. Now that's only good if n is not equal to -1. The reason there's a caveat about -1 is that if you have x to the -1, that's 1 over x, and 1 over x is the derivative of the natural log. So we have to exclude that x could be -1. It can be negative anything else, but not -1. So if we do the power rule, we'll do some examples. Use the power rule to find each one of these integrals. The first one is t to the third dt. So we're just going to apply that rule. That rule says keep your t, add 1 to the t, and then divide by 3 plus 1. See, I think I might already have that one printed out. Yeah, I do. But I'll pull it to the side so I can work each one of these with you. So that actually turns out to be t to the 4th divided by 4. And then just because it's a antiderivative or an integral, we add what's called the constant of integration. So if we have 1 over t squared, remember It's okay if it's -2, so that's equivalent to the integral of t to the -2 dt. So the integral of t to the -2 dt says that we're going to add 1 to the power and then divide by the power plus 1. Plus a constant, which means what our function actually looks like then is t to the -1 over -1, or -1 over t plus c. This is okay. There's nothing wrong with that. But if you're actually going to try to get out of having to have too many parentheses, it'd be easier to pull your negative in front and then drop your t down in the denominator. But you don't have to. It's kind of like taking derivatives. If you can do the integral and get through the first step, you've done the calculus. And then our next one says, take the integral of the square root of u du. Okay, the integral of the square root of u is the same as the integral of u to the 1/2 power. So the way we're going to take its derivative, we're going to take u to the 1/2, add 1 to it, and divide by 1/2 plus 1. And that's going to be u to the 3/2 divided by 3/2, which if you're dividing by 3/2, you're really multiplying by 2/3. So it's actually easier to do that than it is to write 3-story fractions. Okay? Try to keep these different colors so I can keep them separated. So then our last one's kind of tricky. Because it says, what's the integral of dx? What's the only thing we could put between the integral and dx that wouldn't change any value? A 1. Okay? So this is exactly the same thing as the integral of 1 dx, but I still don't see any x's. What's the only way I could put an x in there and still, once again, not change anything? X to what power is x to what power is 1 though? X to the 0. Okay, so this is what's really happening. So then when we take that integral, what we get is x to the 0 minus 1 over 0 minus 1, which is x to the -1 over -1, which is -1 over x, plus a constant. Because you're subtracting 1 both times. You always oh, sorry. Add 1. Brain leak. Thank you. So it's x to the +1 over +1, and that's just x. Now, if you're ever going to memorize one, this will be the one that you'll start memorizing, because you don't want to have to go through this process every time. The integral dx, when there's nothing there, that's just x plus a constant. Okay? It's basically saying the derivative of x is 1. Okay? And in fact, that's how you check your answers. If your function, f of x, is equal to x plus some constant, and you take its derivative, you get back 1. So its derivative, just like it says here, its derivative is just 1. And you can verify every one of them that way. That's the good thing about integration, is that you can differentiate the answer and see if you get back to what you started with. So for example, when we had the integral of t to the third was t to the fourth over 4. If we take that f of t is equal to t to the fourth over 4 plus a constant, that's the same as 1 over 4 times t to the fourth plus a constant, and then the derivative of that is t to the 4 minus 1, and then the 4 comes down in front of the 1/4, and then the derivative of your constant is 0, so 4 times 1/4 is just t, and 4 minus 1 was 3, which checks. So you can always take your derivative to see if you get back your integral. And I'll leave it to you to verify that you can take the derivative of negative 1 over t and come back and find that it was 1 over t squared was the derivative. Okay? And apparently I did not pick up all of my notes because I don't see the rest of them, so let me pull those up. So the next thing we're going to look at actually should make sense to you, because when we did derivatives of things that were added together or subtracted from each other, what we did was we took the derivative of each term that was added and subtracted. Like if we had f of x equals 2x squared plus 2x plus 9, we took the derivative of 2x squared and added it to the derivative of 2x, and then we added that to the derivative of 9. And antiderivatives works the same way. You do it term by term. And that's what this says. So this says to find some integrals and in order to facilitate your being able to see this better, since this printed out smaller on these, I will copy these down. So the first example is the integral of 2v to the third dv. Now this works just exactly like if you were taking derivatives. That 2 sits out front and it just hitchhikes. The actual function is the v to the third. Now in the textbook language it says this is equivalent to taking 2 times the derivative of v to the third dv. And if it helps you to think of it that way, you can, but the way to really think of it is just to remember that the 2 is just a hitchhiker. So when I take this integral, I'm going to take v and I'm going to add 1 to my power and divide by that new power, and then I'm just going to bring the 2 down. And remember to add my constant. So 3 plus 1 is 4. it's 4 here also, and the 2 is the multiplier, so it goes up to the numerator, plus c, which if you want to divide both numerator and denominator by 2, that just becomes v to the 4th over 2 plus c. Okay? And again, I'm going to keep reminding you of this so that you won't forget. If you were to take the derivative of what you get, that would be 4v to the 3rd over 2 plus some constant. We don't know what that was, but we'll assume it was 0. And 4v to the 3rd over 2 is equal to 2v cubed, which is what we started out with. So you should always be able to go backwards. Let's try another one. Part B on the next one. Let's get this up so I can see better. Is the integral of 12 over z to the 5th. And dz, once again, just tells us that what's in front of it's a derivative. So our rules say this is exactly the same as 12, and that's 1 over z to the 5th, so that's the same integral as 12 z to the negative 5 dz. And then our derivative rules tell us that then what we're going to do is we're going to say that's 12 times z to the negative 5 plus 1 over negative 5 plus 1 plus a constant. And that will be 12 z to the negative 4 over negative 4 plus a constant. And negative 4 goes into 12, negative 3 times. So that's z to the negative 4th. And again, that's plus a constant. And probably the book would go on to the step of putting that z in the denominator and saying that's negative 3 over z to the 4th, but I don't care if you do or not. Because at this point, you've done all you need to do. And then our next example is a polynomial. So the polynomial that we have for part C is we're going to take the integral. Pull this down here where I can see. Of 3z squared minus 4z plus 5 dz. And what the rule tells you is you take the integral of the first term minus the integral of the second term plus the integral of the third term. So the integral of 3z squared is 3z to the 2 plus 1 over 2 plus 1 minus 4z to the 1 plus 1 over 1 plus 1 plus 5. We need to add a z to the 0 because we don't have a z and we need one. Over, now that's going to be 0 plus 1, and the denominator then is also going to be 0 plus 1, and then we're going to say plus a constant. So then cleaning it up just a little bit, 2 plus 1 is 3. Four z squared over 2 plus, well, this is just going to be 1, so we're just going to call that 5z. plus a constant. And then 3's cancel, and 2 goes into 4 2 times. So the final answer is z to the third power minus z squared plus 5z plus a constant. So there's the final form. 2, yeah, I left out the 2, thank you, Matt. Okay? Any questions so far? If you pretty well got chapter 12 down by now, chapter 13 or chapter 15 really hopefully won't be that hard because it's basically just applying rules. At least the first section is. So this first one we've got says use the rules to find each integral. And what we're doing here is we're going to need to rewrite this as 2 fractions. Because the bad part about this is there's another way to do it, but the best way to do this actually is to break this up into 2 fractions so that we have the same denominator under both terms. Then we can do each term. So we're going to change this integral to the integral of x squared over the square root of x plus 1 over the square root of x dx. And then to make it even easier still, we're going to change the square root into a power of 1/2. And then we can simplify that first term and just call it x to the 2 minus 1/2, just using your quotient rule for powers, plus 1 over x to the 1/2 is x to the negative 1/2. So really on this one, the hardest part is going to be actually rewriting it into something that we can usually use the power rule on. So 2 minus 1/2 is 1.5, or 3/2. So we're going to treat that as x to the 3/2 power. So that means if we have x to the 3/2 power, the way that we do the integration is going to be x to the 3/2 plus 1 over 3/2 plus 1 plus x to the negative 1/2 plus 1 over negative 1/2 plus 1. And we'll worry about the constant in a few minutes. So 3/2 plus 1 is 5/2. And if this is 5/2, then it would be easier than dividing by 5/2 if we flipped it over and multiplied by 2/5. So the 2 is going to come up in the numerator and the 5 is going to stay in the denominator. So we're going to have 2x to the 5/2 over 5. Plus, this is actually going to be positive 1/2. So when you divide by 1/2, you multiply by 2, so there's going to be a 2 multiplier, and then this is going to be x to the positive 1/2. And that's going to be plus the constant. And you could change it back into radicals if you want to, but I don't care if you do or not. Yes, ma'am? Because up here in this step, you're dividing this by this. And when you divide by 5 halves, you multiply by 2/5. Okay? So that means that the 2 goes to the top and the 5 goes to the bottom. Anytime you don't understand where something comes from, ask, please. Okay? Because generally the question isn't about the calculus, it's about the arithmetic or the algebra. Okay, let's see if we can work on the next one. And since I've kind of covered up my paper there, let me get a sheet of paper to work on the next one. The next one is the integral of x to the 1/2 minus 1 in parentheses and then on the outside of the parentheses is a square dx. Now we'll learn later on another way to do this, because if you look at that, your brain probably says, chain rule. Well, it might have been, maybe, but it's easier to deal with a chain rule problem if all you're doing is squaring is to actually multiply out the function, if you remember. So the way that we're going to handle that one is in a more simple way. We're not going to try to come up with a new rule. The only rule we've got right now is being able to take things that have powers and use the power rule. That's the only one we've got so far. So what we're going to do is change this into something that's just simply powers, which means we're going to multiply x squared minus 1 by itself. And that's going to come out to be x to the 4th minus 2x squared plus 1 dx. And that's easy to find the integral of, because all we're going to do for that one is just apply your rules, which says this is x to the 4 plus 1 over 4 plus 1 is 5. I'm going to stop skipping that separate step. Minus 2x to the 2 plus 1, and 2 plus 1 is 3, plus 1, and remember this wasn't x to the 0 because it's a constant. So this is going to be 1 x to the 0 plus 1 divided by 1. And since 4 plus 1 is 5 here, and 2 plus 1 is 3, and 0 plus 1 is 1, these ones cancel, then our final integral is x to the 5th over 5 minus 2x to the 3rd over 3 plus just simply x plus the constant. Okay? Any questions? So far we have talked about undoing things that we would have basically used a power rule for. Now we need a little bit more. So we're going to talk about how do you do exponential functions, because after we did power functions, we did exponential functions. And basically what this says, and since I'm not using the calculator, I'll make it a little bit bigger so we can all see better. So basically what we know about e to the x is that it's its own derivative, which makes integration of e to the x easier. And the second rule here says that if there's a constant in front of x, then all you do is just keep that constant and then divide by that constant. But the only hitch is, on the next of these, a cannot be negative. It has to be greater than 0. It has to be positive. And a can't be 1. So if you have, rather than e for the base, if it's a to the x, then the derivative is a to the x over the natural log of a. And if we have a to the k times x, just like we did with e to the k times x, we simply carry along the k, but we also have to put the k in the denominator times the natural log. The reason that we don't have to worry about doing that with e to the x, once again, is because the natural log of e would have been 1, and it wouldn't have shown up anywhere. So we're going to do some examples for the e to the x exponential anti-differentiation. So the first example I've got is the integral of 9e to the t. Whoa, that's really huge. Let's get that back down here where we can see it. So that's 9e to the t dt. And the integral of 9e to the t dt, remembering that the 9 is just a coefficient, so it's a hitchhiker. So our integral is just 9e to the t plus c. Okay? If it's e to the 9t, it kind of makes a difference where the 9 is. If it's e to the 9t, then we're going to keep that 9 with the t, but we're going to divide by the 9. And if you think about it, we're really not doing anything differently with 9e to the t, because here what the number in front of t was 1. So if we kept that 1 and then divided by the 1, it didn't change anything. But if it's not a 1, then it does change things. So you need to just kind of think of it that way. And then our next one, lost my piece of paper, is, oh my goodness, 3e to the 4/5 u. It's 5/4? Okay. You've been around me long enough to know that I'm numerically dyslexic. I'll read it and say it backwards. Or I'll read it correctly and write it backwards. So if it's e to the 5/4 u, and I forgot the du, so let me write that down, then, again, the 3 is a hitchhiker. Let it tag along. Still going to be e to the 5/4 u. So then I'm going to divide by the 5/4, which is the same thing as multiplying by 4/5. And then 4 times 3 is going to be 12e to the 5 over 4 u over 5. And after a while, you'll actually stop thinking of this, I think, as dividing by that fraction, and just your mind will say, okay, when that's a fraction, flip it over and multiply by it. Any question on that one? Just don't forget to add your constant of integration, because I'm warning you, my math lab, if you don't put that constant in, it's going to count it wrong. I might be forgiving, but my math lab is not. No, if you don't put the c in, the constant of integration at the end, always put that plus c. And then the next one we've got is the integral of 2 to the negative 5x dx. So once again, the 2 is a hitchhiker. Oops. Well, actually, it sort of is. Let's go back to the rules. Let me pull the rules back over here a second. Just to remind you that what we're doing is, this is an example of A. 2 is equal to A, and this is our power. So remember, we're going to have to divide by the natural logarithm of A. So we have 2 to the negative 5x, which is exactly the same as we've done before. And then we need to divide by the natural logarithm of 2. And then because we have a constant in front of the x, we're going to bring that constant down in front of the natural log. So that's just the process. So that's where that came from. You have to take the natural log of the base. And then just remember, whatever this constant is in your exponent, you drop it down in the denominator as well. That's your process. Okay? Now, have you had any questions on any of these so far, or anything you're not sure about? Okay, we've only got about 5 minutes left. Let me look, see what we've got left. I think we've got quite a bit of this section left. So let's finish up 5.2 next time. I'm sorry, 5.1 next time, and go on into 5.2. Does anybody have any questions about anything? Okay, remember your assignments in Shelby. You've got your chapter 13 and 14 quiz in Shelby that's due on Monday at 11:55. You've also got the last section of 13.3 that you need to get done and get in. At 13.3 is optional. If you're going to do it, you need to get it done by Monday. But you don't have to do it. No, that's just an extra credit assignment.
What's the extra credit?
13.3. You don't have to do 13.3, but it doesn't hurt to do 13.3 because 13.3 is probably the easiest section of chapter 3 in some ways. We didn't really go, I did sort of go over it in class when I gave you the overview of chapter 13. I did talk about what's in 13.3, but we only focused on 13.1 and 13.2. So you can do some of the homework, but I left the due date for the end of class, and I may move the due date out to the next day for 15.1 since we didn't finish today. But you can at least get started on it. If you get started on it, I see that you have, I can go ahead and look and make sure that you're doing okay. But remember, the answers are in the book for all it's just the your turn problems. I haven't posted them yet. And then your exam over chapter 13, 14, and 15 is going to be a take-home test. It is not unlocked yet. I will unlock it when we're ready to do it. But it's going to be due the last Thursday of class, I think. Let me check. It's going to be due on December 6th. So that's the night before the last day of class. That way I can go over that test with you in class to make sure that you understood it. Your final is cumulative, and I will have a study guide for you, and I'll go ahead and post the answers to the study guide. But actually, the best study guide for the final exam is your other exams. That is your absolute best study guide, because there's really nothing on the final exam that you haven't seen on the previous exam. Not one thing. It may not be the identical same numbers, but it's the same problems. Okay? Let's see, we've had what? This will make 3 exams. It's worth about double. It's actually 20% of your final grade, but that makes it worth right at double what any one of the exams is worth. Okay?
So what was on the last test is going to be on the final?
Yes. That's why I want to be sure and go over it with you.
That one's going to be in class.
That is in class. I will tell you how many problems are going to be on it, and I will tell you where to look for examples of those kind of problems. I'll be pretty specific about what you need to go do. Okay? Because I know it's coming down to crunch time.
Shobies are kind of mixed up.
Did I put them in the wrong folders?
You put the 14.4
In
the
14.3?
implicit differentiation one in 14.3 and the
Okay, and
elasticity in 14.4.
Yeah, I need to switch them. Well, what I'll do then is I'll just go back and switch the name of the folder.
Well,
Which would be-
I put the pictures that I took from my 14. The actual 14.3 elasticity stuff in the 14.3 folder.
Okay.
But
Yeah, that's fine.
that doesn't throw you off.
No, it won't. I didn't realize that. Thanks, Scott.
Yeah, I figured you want to know about that.
Yeah, I'll have to fix that.